All right, so let's see, number 20. This is very similar to homework 12, problem 5. In number 20 in particular, we are asked to find the inductor current IL at T is equal to a very specific point in time. So writing Kirchhoff's current law, we can say that IS of T is equal IC of T plus IL of T. And we can also see that IS of 0 is equal to IC of 0 plus IL of 0. Since we want the inductor current specifically, our inductor current is going to be, let's see, IL as a function of time is 1 over L times the integral from T naught, which is at 0, to some later point in time T, of our source voltage Vs of T prime dt prime plus IL of 0. Vs of T is given to us. Is of 0 is given to us. And IC of 0 is the answer to number 19, or IC was effectively found by working number 19. The reason why that's important is because we would need to use that information to find IC of T. And so we have everything that we would plug into the equation. At this point, it's just putting it into the calculator. So if you were struggling with 19, IC is C d Vs by dt, and from this IC of 0 is C d Vs by dt evaluated at 0. And then it's the same thing as homework 12, problem 5. Next question. Yes, Ryder. Yes. Changing magnetic field. Yes, Brody. All right, so the switch is closed at position A for a long time. So at T is equal to 0 minus, there's a short circuit right here, right? At 0 minus, our capacitor looks like an open circuit, which means there's a 0 volt drop across our 4 ohm resistor because it's not part of a closed current carrying loop when the capacitor looks like an open circuit. So if we were to write a Kirchhoff's voltage law equation around this loop, or I guess technically, we would have -7 minus VC is equal to 0. So -7 minus VC is equal to 0. VC is equal to -7, and we're done. Next question. So we're finding the Thevenin equivalent between A and B. So let's define our Thevenin voltage as this voltage. Do you have a preferred analysis method for me to use, or do you want me to just use whatever I feel like? So I'm going to be lazy, and I'm going to make node B ground and do nodal. So this is A. This is going to be C. This guy down here is going to be D. I don't have any dependent sources to worry about, so I don't have any controlling variable relationships. I do have a voltage source, so I'm going to have 8.4 volts is equal to VA minus VD. I have a super node that I'm going to have to write a KCL equation for, so let me explicitly state what currents I'm going to be adding. So this current leaves supernode AD, and this current leaves supernode AD. There is a current that's flowing through the 11 ohm resistor, but it's all flowing both down and up from the supernode, so they cancel each other out. I don't need to write it. Effectively, anytime I have a resistor in parallel with a voltage source, I can just lump that in with my supernode, and it doesn't change anything at all. So my KCL expression for supernode AD is going to be 2.1 amps plus VD over 7 ohms is equal to 0. Solve this system for VA, and VA is VTH. Next question. Why did I make D what?
Why should you make it?
So that B is the negative polarity terminal of my Thevenin voltage, so that if I find node A, I find VTH without having to do anything extra, just purely laziness. Katie. Winter 2019, problem 30. All right, so let me scroll up here. So problem 30 is the only part of this that you aren't able to do. So let's glean some information here then. So IL at 0 minus has to be equal to IL at 0 plus was 1.875 amps, which you didn't have a problem with. So let's see. The IR at 0 plus was 2.058 amps. I'll have to come back to that in a second. IR at infinity was 2.667 amps. So IR of T is going to be 2.058 minus 2.667 e to the negative t over tau is 65 milliseconds plus 2.667 amps. And then t is given right here. So let's see what happens if I throw this into the calculator. Always a possibility that I made a dumb mistake. 47.161 over 65 plus 2.667, 2.372. Yeah. Yeah. So the generic equation, let me scroll down here, is y of t is equal to y of 0 minus, or t less than 0 minus, and it is y of 0 plus minus y at infinity e to the negative t over tau plus y at infinity for t greater than or equal to 0 plus. Or a e to the minus t over tau plus b, according to the lab thing that we worked the other day. Same equation. Yes, Brody. All right. So since this circuit is looking for the Thevenin resistance and there are no independent sources, I'm going to have to use a test source method here. So give me just a moment to think about which one I want to use. I'm going to use a test. I'll use a test current source. I want to see how this plays out. So I'm going to need to find this test voltage, and I'm going to make this node A, B, C, like so. So Vx is just equal to Vb minus Va. Then I will have Va over 2 plus Va minus Vb over 4 is equal to 0. Vb minus Va over 4 minus 0.7 Vx plus Vb minus Vc over 9 equal to 0. Vc minus Vb over 9 minus 1 equal to 0. And then R Thevenin is Vc over 1 amp. I chose to do nodal analysis there because I was trying to find the voltage specifically. I chose to use a test source because I was originally thinking about using mesh analysis here, and I wouldn't have to write a KVL equation if I chose a test current source there. But then I thought, well, if I'm solving for voltage, I'm just going to do nodal, and because I won't have to do any thought after the fact. So this is one of a multitude of different ways you could do it. You could use a test voltage source, you could use mesh, you can do whatever the hell you want, but this way got you what you're looking for. Yes, Jonathan. 26 on summer 2019. All righty, so our switch has been open for a long time. So effectively, all of this crap over here is not connected to our source, so it's 0. Because the switch was open. So if we do Kirchhoff's current law at this node, we know that the current flowing down here is 10 milliamps. And the current flowing here is 10 milliamps, which means this current must be 0. Sure, so at 0 plus, and we're looking for V of t. All right, so let's see. So at 0 plus, this is closed. Since our inductor current was 0 amps, we need to replace our inductor with a 0 amp current source, which is an open circuit. And so using current division, let's see, I'm going to call this current IX real quick. So using current division, IX is going to be 10 milliamps times. So I have in series with 2 kilo ohms. So that is going to be 1/3 plus 2 divided by 1/5 plus 1/6 plus 1/3 plus 2. Once I know IX, V of 0 plus is equal to IX times 3 kilo ohms. And then there's a negative sign out front because the current that I've labeled IX is flowing into the negative polarity terminal. What's next? Yes. Number 25. All right. So let's call this guy ER, this guy L. Let me think about this. So that the current is flowing into the positive polarity terminal of everything so that it's all absorbing power. I don't know that that's particularly important here. Let me look at this guy real quick. So we're trying to find the capacitor voltage. So let me think about this. And we need the, okay, so if we're trying to find the capacitor voltage, let me write down our capacitor equations, right? So IC is equal to C dV by dt. And VC is equal to 1/c times the integral from 0 to t of IC t prime dt prime plus VC at 0. we want the capacitor voltage, so this is the one that we're going to have to use. We know C. IC is just IS, so the only thing that we don't have here is VC at 0, right? We were given VS at 0. So Kirchhoff's voltage law around this loop tells us that VS of 0 is equal to VR of 0 plus VC of 0 plus VL of 0. VS of 0 was given to us. VR is just going to be 5.1 kiloohms times IS of 0, which is 18 milliamps. VL of 0 is going to be, let's see, L, which is 25 millihenries times the derivative of IS of t evaluated at t is equal to 0. Let's play around with this a little bit further here. All of this, and then we would have e to the blah, 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 but that's going to be at 0. So VL of 0 is 25 millihenries times negative 2500 per second times 18 milliamps, and that should get us that voltage. Now that we have VL at 0, VR at 0, and VS at 0, we can solve for VC at 0, plug it in here, and we have all the information that we need. So I believe that one is similar-ish to homework 12, problem 3. All right, so for this one, we were given the voltage drop across a 610 microfarad capacitor. We are asked to find the capacitor current, so let's write down our relationships up here. I is equal to C dV by dt. V is equal to 1 over C times the integral from T naught to T of IC of T prime dt prime plus EC at T naught. Sorry, I ran out of room there. We have voltage and we're trying to find current, so we're going to use this equation. So for T is equal to 14 milliseconds, we just need effectively this slope, which looks to be -6 over 4 milliseconds. Multiply that by 610 microfarads, and that is our current. Then we want the power at 2 milliseconds. So we have the voltage, we need the current. So our slope here is 2 volts over 4 milliseconds times 610 microfarads. So that gives us our current. Our voltage is 1 volt. That's our power. And for number 21, the energy stored at 6 milliseconds, we're given the voltage Here's 6 milliseconds. So this is just going to be 1/2 610 microfarads times, so 1/2 C. V is 2 volts squared. The other option would be, if it wasn't the derivative-based relationship, we'd have to use the integral-based relationship, and then we'd be taking the area under the curve. And these, all of the curves that you would possibly get are just going to be right triangles or rectangles. So I should not have to repeat this, but the area of a right triangle is 1/2 the base times the height. The area of a rectangle is the base times the height. Say I shouldn't have to repeat it, but I did have a group of students over one summer who almost half of them could not remember how to take the area of a triangle. So I'm just going to give you guys the equation so that nobody has to ask. Brody. Number what? 33, thank you. So for 33, we're evaluating what's going on at t is equal to infinity. So at t is equal to infinity, that's a short circuit. This is an open circuit. So let's think about things from this perspective, right? So if this is our reference, I know that this is 6 volts. I know that this node is 4 volts. So this current right here is going to be 6 volts minus 4 volts over 2 kiloohms. And then I can do KVL around this loop, which would give me, so let's see, -6 volts plus 2 volts over 6 kiloohms plus V at infinity is equal to 0, and then I would solve for V at infinity. I made a mistake there. I made a couple of mistakes here, actually. Sorry. So the 6 kilo ohm resistor and the 2 kilo ohm resistor appear as if they're in series. So that should be 8 kilo ohms there. That should be 8 kilo ohms there. And then it works out. So sorry, I put the two different resistor values instead of combining them. Oh, 33 is asking for the current. All right, sorry about that. So the current is easier. It's negative what I just wrote down there. Number 15. All right, so we want the energy stored by the inductor. So let's start off by recognizing that this is a DC circuit. So our capacitor is going to look like an open circuit, and our inductor looks like a short circuit. So effectively, any current that's leaving the positive polarity terminal of the 46 volt source is going to flow through the 17 ohm resistor here. None of it can branch off and flow to the right because the 12 ohm resistor isn't part of a closed current carrying path. All of it is going to flow this way. Then we have a short circuit or a 9 ohm resistor, so it's all going to flow through the short. So if this represents our current IL, we can say pretty easily that IL is 46 volts over 7 ohms plus 17 ohms. And the energy stored by the inductor is 1/2 L IL squared. Anybody got beef with that? Next.
Voltage drop across that has to be the same as the voltage drop across.
I believe so. I don't think that's how that's not where my brain jumps to. So once I know IL, I have this voltage. And so I could do KVL, let's call this VC here. And so I could do KVL around this right-hand loop. That being said, because the 12 ohm resistor doesn't have a voltage drop over it, the capacitor does effectively appear to be in parallel with the 7 ohm resistor. So that is an easier way to do it. Sure. So it would just be 7 times IL. Should get you the same answer as the way that my gut reaction tells me to do it, which is slightly longer. Yeah. So we need our capacitor voltage here. So this is an open circuit. Let's call this VC. This is a short circuit. I'm trying to think of if I can use effectively laziness to get the answer. I believe the short answer is yes. I'm just trying to figure out how to do it. And whether or not I want to bother doing a source transformation over there on the right-hand side or not. No, I'm going to do something different. I'm going to call this voltage here Vx and choose this thing as my ground. So from here, I could say that Vx minus 24 volts over 21 plus 7 plus Vx over 14 ohms minus 3 amps is equal to 0. Solve for Vx. Vc is just going to be Vx minus 9 volts. just in case you guys are wondering about stuff, I'm lumping my 21 ohm resistor and 7 ohm resistor into a single resistance, thereby eliminating a node and making the math involved easier. I feel like we're all hopefully comfortable enough with resistor combinations to do that, but just in case you're wondering what sorcery I am writing down, that's what I did. So that one is my inductor current. So my inductor current is this current right here. Let's call that IL. So we know that this current right here is Vx over 14 ohms. This current right here is 3 amps. So we can write a KCL equation that says IL plus Vx over 14 is equal to 3 amps, and then solve for IL, and then 1/2 LIL squared, good to go. I don't know. Oh yeah, so you could just do Vx minus 24 over 28. That also works. So this is, you're saying, why doesn't this current show up in my equation? Because the current flowing into this node is equal to the current flowing out. So I'm treating it as effectively, this thing is a node. I could say that IL is equal to Vx minus 24 over 28. Or I can say that Ix is equal to 3 minus Vx over 14. I'm double counting it if I include the thing on the left in my original expression. Because that's the way I drew my arrow, purely just, I drew it and that's it. Doesn't matter. So Vx is a voltage between this node with respect to ground. The voltage here is 9 volts with respect to ground. So that's effectively almost like me doing a Kirchhoff's voltage law equation around that loop. Voltage present at the nodal voltage present at the positive polarity terminal minus the nodal voltage present at the negative polarity terminal. So the voltage at this node is 9 volts with respect to ground. The voltage at this node is Vx with respect to ground. And then I'm just using basic nodal analysis way of writing a voltage drop. As far as I know, yes. I haven't heard anything contrary to that. I will confirm that with Ashley Osborne in a few minutes. Yes. Oh, sorry.
curious, would it help simplify anything, finding the source, well, changing the current source to a voltage source?
So I thought about doing that. That would make solving for IL pretty straightforward. So if you did a source transformation on the right-hand side, then you could effectively just write a KVL equation around the outside loop, because all of those, the 7, the 21, and the 14 will all appear as if they are in series. And so then it's just going to be 24, minus whatever 3 times 14 is. Should probably 52. Sound about right? Maybe, I don't know. Divided by those resistors gets you IL. And then you could just do KVL around this leftmost loop to find VC. So sure, nothing remotely wrong with that. In fact, if I were doing 11 first and then 12, that seems like one of the easiest ways to do it. You could always also just do mesh. What's next? All right.
So I understood the way you make them on the solve thing.
Mm-hmm.
I was just wondering, since you give you Vx as the Thevenin voltage,
Mm-hmm.
and for the IN, it would just be 6Vx.
For the I what?
The Norton current.
So Norton current doesn't mean anything here because we don't have any deep independent sources. We are asked to find the Thevenin resistance specifically because there is no independent source. The Thevenin voltage is 0 and the Norton current is also 0. There's nothing exciting the system until we apply a test source. So that's why we have to use a test source. Anytime you only have dependent sources and no independent sources, you have to use the test source method. Yep, that is exactly what I would, for this particular problem, using a test voltage source makes this trivial. So if we put a 1 volt source here, then we know that this is 6 amps flowing down. This is 1/16 ohms. And I test is just those 2 things added together and we're done. So for this particular one, using a test voltage source makes this much, much easier than if you'd use a test current source. Next. On this test or a different test or?
Oh, yeah, that's all.
All right, Thevenin voltage. So let's see what we get here. So I'm going to do nodal analysis. I'm choosing this node as my ground. VA, VB, VC. Vx is VA minus VB. VC is 2Vx. KCL at VA looks like -5 plus VA over 4 plus, out of the way, zoom thing, VA minus VB over 8. KCL at B is VB minus VA over 8 plus VB minus VC over 10. Solve, solve, solve. VB is 3,000. For Norton, I would short A and B and then just do mesh. Do I need to go through the steps of writing mesh out for that? I would think if people made a mistake on this problem while doing nodal analysis, remembering that that's a node is probably the most common mistake.